Yeah, thank you very much. And I would also like to thank the organizers for inviting me. So, what I would like to talk about today is about restarting algorithms. And the basic idea here is to restart algorithms to basically harvest some type of performance improvement. This talk is going to be a bit of an overview talk. I try to not go too much into technicalities, but rather to give you a bit of an idea of why restarts can be useful. All right, so what is this talk about? This talk is about the deliberate restarting of algorithms with the aim to significantly improve algorithms' performance. And so what I will give today is a brief overview of restarting. And the focus here will be on restarting with provable guarantees that we actually get some form of improvement. And in terms of outline, I will first talk a bit about restarting in general, then what it does and why it works, and then maybe also why sometimes it should not work. I will then present an example or examples from convex optimization where we can obtain better rates by restarting. So in some sense, convex optimization is one of the prime examples here in this context, because in convex optimization, restarts have been used in many different contexts already and are quite a well-established and well understood technique. The second example here will be about discrete optimization and how we can optimize faster by using some form of restarts. A quick disclaimer, so today I'm going to focus mostly on optimization, but similar approaches work in many different areas and have many uses outside of optimization. Also, I try to present as few technical details about the base algorithms that we are going to restart as possible, in particular because typically restart schemes are somewhat black box and don't really need to know that much about the algorithm that they're restarting. And you can think of this as being a feature of these techniques. So what is very important, the references that I'm going to provide today are by far not exhaustive, and I would recommend that you check the references contained in those that I cite, as well as those that I have included in the extended abstract. Okay, good. So having said that, what is restarting? So restarting is really what you think restarting is supposed to be. It's a deliberate restart of an algorithm in the hope of improving performance. So how does this typically look like? So here's a very simple restart scheme. So let's say we do this in the context of optimization here. So you have maybe some initial point x0 in Rn, some base algorithm A that we treat here as a black box, and then maybe some iteration counts TL and some function f. And what this algorithm, this scheme is outputting here is iterates x1 to xk according to the number of restarts. And we basically have a for loop that runs the base algorithm for a fixed number of iterations, TL here, and then takes that output and feeds this as input in the next restart phase. And that's really what restarting is in its most basic form, of course. So what happens when you restart? So obviously the algorithm that is restarted starts from its beginning in some sense, and the internal state of the algorithm is reset. That in particular means that you usually lose some already collected information. On the other hand, you might elect to carry over some of the information, as we, for example, do up here in this simple scheme, by feeding that information that you have collected into the next run of the algorithm here. And so what's happening on maybe a slightly more informal level, you hope to better condition the algorithm, for example, in terms or in the form of randomization maybe. So these are all different things that might happen when you restart the algorithm. Then a very natural question to ask is, what does the research really do to the algorithm on a more, let's say, metaphysical level? So what restarting achieves is the following thing. So suppose you have built an algorithm and you have some algorithm designer that built that algorithm with some structure in mind. And now you apply this algorithm to an environment where more structure, exogenous structure, is present. And so what you can very often do with restarting is you can make that algorithm that was not designed with this additional structure in mind sensitive to this additional problem structure. And the way this will happen, as we will see, is really in a black box type of fashion. So we don't really need to understand that much about the base algorithm. And still we can use these restarts to incorporate this exogenous structure into the algorithm. So why it works and why it should not. So restarts typically work because we left something on the table in the initial algorithm's design. That usually is an indicator that we should have included maybe this additional structure directly into the algorithm, although in some cases there's actually such an integration is unknown, and the only way of how we can reap these benefits from improved performance is really by means of restarts. Typically, restarts cost you a little compared to the optimal algorithm without restarting. But this overhead is typically quite insignificant, usually a constant factor or maybe a lag factor, depending on applications. And what is also very important, and we'll come back to this later, is that restarts very often explicitly depend on some parameters that describe this external or exogenous structure here. But we'll see that there's ways to deal with this and basically circumvent the issue of knowing these parameters. So let me give you a few examples where restarts have been used traditionally. So there's many cases where restarts have been working empirically very well, although we do not have strong theoretical guarantees that explain why this is the case. So there's many cases in set solving and constraint programming where we use restarts, for example, to explore different parts of the feasible region, or we maybe learn some clauses that we want to reintegrate. So we learn clauses, we add them to the original formulation, and we restart. Then there is global optimization, where restarts are used usually by randomizing the initial points in order to explore different parts of the search space and potentially ending up with different local optima. Then we have integer programming, where restarts are strongly inspired by restarts in the set and CP community. But there's also other cases, such as, for example, the recent clairvoyant restarts that are based on tree size estimation. So these restarts are really, like, in terms of working empirically, usually quite well, but at the same time often, but not always, lacking strong theoretical guarantees. And then we also have restarts that tend to work empirically very well and that also come with very strong theoretical guarantees. So there are, for example, there's variance reduction, which is often used in stochastic optimization, and that can improve convergence rate dramatically. And here the idea is that you basically, it's called checkpointing. So you checkpoint the gradient, which means that you once in a while you compute an exact gradient, and you use this exactly computed gradient to reduce the variance of your gradient samples that you would use in the other iterations, and that helps a lot with the variance and basically makes convergence significantly faster. And then we have acceleration in convex optimization. This can be in different contexts. It does not just have to be Nestrov's type of acceleration, but there's many cases where we have auxiliary structure, and by restarts we can dramatically improve not just theoretical rates, but also the empirical performance of these algorithms. So there's many examples. If you want to have a few extra examples, please check out the extended abstract in the proceedings, where I have many more examples of what you can do with restarts. Okay, good. So let's start with our first example here. That's restarts in convex optimization. Let's maybe recap a very few basic notions here. It's really like just the bare minimum that we need to understand what's going on. So let's say we have a function f, that let the function be differentiable. Then we say that this function f is basically convex if at any given point x you can build a linear underestimator for the function. Think of this as the tangent that you put at a given point, and that gives you a linear underestimator. That's really what convexity is about. In particular, it also implies that all local minima are actually global minima. Then we have the case of L smoothness. So here, the way of how you want to think about smoothness is it makes sure that the gradients of your function f here are not too crazy, or put differently, that at any given point x, you can put a quadratic overestimator at any given point x that bounds the function from above. Yeah, so what this looks like in picture world is what you see here. So let's say this orange one is our function f here, and then we have our underestimator here in blue, and we have our overestimator from smoothness here in green. So that's a quadratic, and that's a linear function. So, and yeah, so that's just to recap a few basic notions. And what we are interested in doing now is we want to solve the following optimization problem: minimize f of x, f being, let's say, unbounded, where the function f is convex and L smooth. So that's a very simple optimization problem, and that's the only thing that you know for now. And so whenever you see something like this, there's a natural approach to achieve the optimization here. So you could, for example, run gradient descent. And gradient descent really means that you update or build your new iterates xt plus 1 by taking the old iterate xt, and then you subtract 1 over L times the gradient of f at xt, and that gives you your new gradient, your new iterate. And yeah, so that's just standard gradient descent, nothing too special here. And the standard guarantee for gradient descent for the smooth case states that whenever you have an initial point x0 and an optimal solution x star, then the primal gap here, so the f of xt minus f of x star, that's the primal gap after t iterations of the algorithm, is upper bounded by the distance of the initial point to the optimal solution squared times some constant, so the constant here is L, divided by t. And that's the standard guarantee that you get for smooth convex optimization. So that's all that you have. All right, great. Now it turns out that the function f that you had is actually not just convex, but it turns out that this function is actually also strongly convex. So what does this mean? That means that you do not just have the linear underestimator in blue here, but you actually also have a quadratic underestimator here, the one in red. And what you see here is the strong convexity inequality, and it's basically the same inequality as the smoothness inequality, except for you turning the inequality sign here and you're replacing the L by a mu. So you have now a quadratic from below, and you have another quadratic from above. So why do people typically care for strong convexity, apart from it giving you a bit of stronger estimates or better structure? Well, it allows you to relate the distance to opt, which is an error measure, so the distance of your current iterate to the optimal solution, to the primal gap. Namely, what strong convexity gives you, just by plugging it into the definition, is that the primal gap here, that's what we see here, is lower bounded by the distance to the optimal solution squared times mu over 2. So that's what you get from strong convexity. So, and yeah, so why is this useful? Well, this brings us to the first restart setup that we are going to consider. Namely, the idea of restarts almost always is the chaining together of two error bounds. And we have two error bounds here. So the one is from the original guarantee that we have seen, that is basically the primal gap, so f of xt minus f of x star. And the second error bound that we have is the distance to opt, so that's the norm of x minus x star, or xt minus x star. And whenever you have two such error bounds, you can very often chain them together in the following way. So we start out with our convergence guarantee that states that f of xt minus f of x star is upper bounded by the distance of the initial point to the optimal solution squared times L, that's our smoothness constant, divided by t. So that's just the guarantee that we had from smoothness. And then for this term here, up here, we plug in now the estimation that we just had from strong convexity. So what this means is basically that this is upper bounded by 2 times L divided by mu f of x0 minus f of x star. So that's our initial primal gap divided by t. So that's just chaining in the primal bound that we get from strong convexity. And now we assert that we want to run our algorithm until the primal gap here, that's the initial primal gap, is reduced by a factor of 2. So we want to halve the primal gap. And for this, we just solve the equation here, or the inequality here. And we see that we halve the primal gap after about 4 times L divided by mu many iterations of our standard gradient algorithm here. And that's in particular a constant number, so please keep this in mind for the estimation on the next slide. So what we can do now is we can basically run our algorithm for 4 times L divided by mu many iterations. That gives us a new iterate, say, let's call it xt. And then we use this as an input and restart our algorithm. So let's see how this looks like. So this is that's basically the same restart scheme that you have seen in the introduction, but now we look at it for the specific case of gradient descent. So our base algorithm here is basic gradient descent. And we run this for 4L over mu iterations before we restart. So that's what you see here. We do k of these restart phases, and then we always output xl, which is the output of our algorithm A, which is just gradient descent applied to f, starting from the iterate from the last iteration and running for 2tl many iterations here. And let's see what we get from this restart scheme. So in order to reach an iterate xl with a primal gap of at most epsilon, we have to halve the initial gap x0 from f of x0 to f of x star at most k times, where k is essentially the logarithm of the initial primal gap divided by epsilon, right? So that's how often we have to halve to reach a point where the primal gap, the new primal gap, will be at most epsilon. And moreover, we have seen that in each of these restarts phases or runs, we run a constant number of iterations, namely 4 times L divided by mu. And if we put this together now, we reach an iterate xl with f of x star minus f of x star being at most epsilon after basically 4L divided by mu times logarithm f of x0 minus f of x star divided by epsilon many total iterations, and that's O of L over mu times log initial gap divided by epsilon, which is exactly the guarantee that you would expect for the smooth and strongly convex case without any fancy things going on here. And that's of course much better than the rate that we just got for the smooth case, which is just 1 over epsilon. So we got an exponential improvement here by restarting the algorithm. All right, good. So let's see. Now let's maybe revisit what we have done for a second. So the gradient descent algorithm that we restarted was defined as xt plus 1 being xt minus 1 over L times the gradient evaluated at xt. And if you look at this very closely, then you will see that this is memoryless. And what I mean by that is that there is basically nothing that this algorithm saves, and it's completely stateless. And in particular, when you restart this algorithm, the iterates are not going to change. They will be exactly the same as before. And what this means is that we have accidentally actually also shown that gradient descent without restarts converges linearly for strongly convex functions, even without knowing anything about convex optimization, right? So this is just a byproduct here. Let me stress, though, that this was now due to the purposefully chosen example here. And typically, it's not just that you get a better guarantee, as we did in this case here, but you actually also get a better algorithmic behavior. Let me convince you of that. So let's consider the following function here. So f of x comma y is minus y to the 3 plus x squared minus y, everything divided by 3 here. That's purposefully a slightly more interesting example. So that's that function is non-convex, and we use a non-convex variant of gradient descent just to make it a bit more interesting here. And so what you see here is the convergence behavior on that surface. So the blue one is the gradient descent algorithm that we use here without restarts. And then you have the red one that makes much more progress. So both of them ran for 120 iterations. So you can see that there is something going on here. And we can also see that if we actually look at the primal gap, then we see that the algorithms behave the same in the beginning. And then the red one is restarted, and you see that it continues much faster here with these restart bumps towards the optimal solution compared to the non-restarted algorithm here. And that's very typical behavior for restarted methods. Actually, you can very often spot if there is some form of restarting going on within an algorithm if you see these types of restart bumps here. So in summary, it's not just about proving better rates. Yes, sometimes this happens as well as in the simple example, but usually you actually change the behavior of the algorithm and you do obtain faster convergence rates because you change the algorithm's behavior. All right, good. Now that we are quite happy, right? So we have obtained this algorithm that we obtained by restarting, and it's converging with a linear rate for strongly convex functions, and we happen to run into Nesterov. And Nesterov is going to tell us, well, that's great that you use gradient descent here, that you restart, but actually that's not the optimal algorithm. You can do much better if you use my accelerated gradient descent. And then you ask him about this method, and he's going to tell you that this method is somewhat more involved, and in particular it's not memoryless anymore, and you need to maintain very specific weights of the iterates and how they interact with each other. Also, the algorithm is not as easy to state anymore as in the case of gradient descent, and it's also not that easy to understand. In fact, up to this day, acceleration is one of the most perplexing and well-studied topics in convex optimization because people don't really fully understand why this phenomenon really occurs, or there's many explanations, but there's a lot of mystery going on in the context of acceleration. Nonetheless, Nesterov is going to tell you that there exists this guarantee that states that if you have your initial point x0 and you pick an optimal solution x star, then now the primal gap contracts as the initial distance to opt squared times L times some constant c, divided not by t but by t squared. So you get an exponential improvement, a quadratic improvement by using Nesterov's accelerated method here. Unfortunately, you know nothing about the algorithm, and we also don't really very much understand how this works. But luckily, because we are in the context of restarts here, we don't really care that much for the base algorithm and just use it as a black box. So we just try to repeat the argument as we did before. So we start out with the primal gap guarantee that we get from Nesterov's theorem that states that the primal gap converges as distance squared divided by t squared, basically. And then again, we chain in the strongly convex guarantee that we had from before. So we get 2cl divided by mu times the initial primal gap divided by t squared. So that's basically the same thing, except that we have a t squared now and we have the c up here. And again, we assert run until we halve the initial primal gap. And then in a very similar fashion, we can solve the above. And we obtain that the number of iterations t that we will be needing is not 4L by mu anymore, but square root of 4 times CL divided by mu. So we need quadratically fewer iterations per restart phase in order to halve the initial gap. And then we do the same thing, we restart the algorithm and just use the iterate output from the previous iteration or restart as input for the following one. That's basically the algorithm. And so we run this restart scheme, but now we replace gradient descent by the accelerated gradient descent here, and we have a different number of restarts or runs per restart. And let's see what happens if we run our convergence analysis. So in order to reach an iterate XL that is sufficiently close to the optimal solution, we have to halve the initial gap again, basically initial gap divided by log initial primal gap divided by epsilon many times. And now each restart run runs quadratically faster, so we need only root 4 times CL by mu many iterations. And then we can again put everything together, and then we obtain that the overall method now runs not in L times mu times log primal gap divided by epsilon, but we have a quadratic improvement in the condition number, so that's the condition number here, and we obtain that the method now runs in O of root L divided by mu times the logarithm of the initial gap divided by epsilon. And that's much faster, and for many, many applications it makes a huge difference. And in fact, this turns out that this is the optimal rate and the best that you can do. Yeah, so that's basically what we obtain when we now restart a Nesterov variant. Now, of course, you might say, well, that's all very nice, but in order to perform these restarts, in both cases, we need to have knowledge about L and mu, because we set the number of inner iterations, in one case being 4 times L divided by mu, and in the other case being a root of 4 times C times L by mu. And in fact, you might even have to estimate the C, but you can get around that one a bit easier. All right, so that's basically what we have used. And now, in reality, these parameters that we require for setting the restart schedule are usually not observed. And if we use slightly more interesting structural properties such as sharpness or Hölder error bounds or gradient-dominated properties, then they might be actually highly dynamic, and they might depend on a ball that you put around the optimal solution, many, many other things. So basically, you are not going to know these parameters ahead of time. In this case, you can do two things. So one thing that works very well in many applications is that you can use a so-called error measure. So for example, you can use the dual gap or maybe some other measure that you have. And you observe that measure and you restart when you have the gap in this error measure now. And if the error measure is converging essentially at the same rate as the main algorithm, then this is sufficient to obtain optimal restarts rates, provided that you can actually do this with restarting in first place. The other thing that you can do, and that's what people have been doing more recently, you can use adaptive restarts. So the way of how you want to think about this is it's some form of a search strategy that searches for a good enough restart point. And if you do this, think of this as being some form of a smartly done binary or grid search that usually costs you a log factor. So you don't get exactly the optimal rate, but then at the same time, you don't need to know the parameters. Yeah, so the key question, of course, is now whether this actually still works in reality. And it turns out it works very well. So here's two examples. The first one is from one of the earlier papers from 2012, where we have our initial algorithm here in blue. Then we have the accelerated variant in, the initial algorithm is in black, the accelerated one is in blue, and then you have two forms of restarted variants here. One's restarted by a scheme in function value that estimates the restart point, and the other one in the gradient, and you can see that they perform much better than the original one and the originally accelerated one. And then on the right, you see again some form of restart scheme that is adaptive from a pretty recent paper. And there you see in green the original algorithm, you see the accelerated one in pink and blue here, and then you see the one with the adaptive scheme in red. And that's very often because if you run these accelerated algorithms and you estimate the parameters in a suboptimal fashion, you might not converge at the optimal rate, and you might have to take a worst case estimation for these parameters. All right. Now, in the following, I would like to talk about restarts in discrete optimization. That's a bit different from the convex world, where we understand things very well, and restarts have been a very important techniques for many years. In discrete optimization, it's a bit on the newer side, and also not that often used as of now. So our starting point is the following. So we want to consider a basic integer programming problem. In fact, we want to solve maximize Cx, where x is in some polytope p and has to be integral. In order to simplify things here, let's assume that p is actually contained in the Z1 cube here, and that our objective function is non-negative. But that's really just for the sake of exposition. You can relax these assumptions one canonically and the other one I'm going to talk about a bit later. All right, so that's the problem that we want to solve. Unfortunately, we don't know anything about integer programming. Let's at least assume this for now. And however, the only thing that we do now is we have some method that if you give me a solution X and that solution happens to not be optimal, then I'm able to make it a little better. So maybe I have a heuristic or something like this that improves over the current solution as long as it's not optimal. Yeah, so that's basically what we have. To make this a bit more formal, in terms of what this incrementally improving means, we assume that we can augment the solution. So what does augmentation refer to? It's a very basic algorithm. So you have some initial feasible solution x0, and you have some objective function c. And what this algorithm does is it successively improves the solution, outputs an optimal solution here to the optimization problem, and it does it in the most trivial way. So you start with the initial point, and as long as this point is not optimal, which is just what this condition says here, so you can improve, you just take an improving point x and just update. Okay, so as long as you're not optimal, you find a solution that is a bit better, you update, repeat. That's really what augmentation does. As you can imagine, that's not rocket science. Augmentation can be very slow. So these incremental improvements can potentially lead you to enumerate all 2 to the n solutions. Just think of an objective function that induces a total ordering on the 0, 1 points, and then you will enumerate all points of the 0, 1 cube here. That's of course not so great and potentially very slow. However, what we're going to do now is we're going to use a very simple observation that allows us to dramatically improve the augmentation algorithm here. And to this end, we decompose the objective. So we do this in a way that we bit decompose the objective. So assume that you have your objective C here. And what we do is we write this as 2 times C1 plus C0. And C0 is a 0, 1 vector. So basically, we chop off the least significant bits, and then we can encode the original objective with fewer bits. So we just write it in this form here. All right, so we have done this. And the reason why we do this is because there's a key observation here to be made. Namely, suppose that you have a solution x0 that is optimal for the optimization problem where we do not maximize c, but c1. So we maximize c1 times x, where x is in p and integral. Now, if we take any other point in the feasible region and we check by how much this could be potentially better than the point x0 that was optimal for C1, then we see the following thing. So we just write this as 2 times C1 x minus x0 plus C0 x minus x0. This is just like plugging in what we have here. And then we observe that the first term here is non-positive. Why? Because C0 was optimal for C1. So this basically goes away. And now the second term only involves 0, 1 vectors, so it's at most n. And that tells us that when you're optimal with respect to C1, with some point x0, then any other possible point here can have at most a residual gap of at most n. And once you have this, what you can do with this is more or less automatic. Namely, what we will do now is we devise a restart scheme where we restart via the objective itself. So what do? We run the augmentation algorithm on, let's say, the highest or the most significant bits first. And then when we are done, we obtain an optimal solution for that. Now we multiply this objective by a factor of 2 at the next bits that we need and rerun our algorithm. So that's exactly what is happening here. It's just written in a slightly more complicated form. So we start with the most significant bits. That's what's happening here. We call our augmentation algorithm to optimize that. So that takes at most n iteration steps. So it's relatively efficient. And then what we do is we halve the mu here and we update the c mu here as the c divided by mu rounded down. And that just means, like, if you can do the calculation, that we add the next bits in the decomposition here. And then we rerun this. And by the argument from before, this takes at most n additional steps after rescaled. And we run this until the mu here is less than 1. And then we return the point that we have obtained. So that's the bitscaling restart scheme here. And what this does, just to give you an idea in this 2D visualization here, so we have our feasible region, that's the circle here. That's our initial point, that's the optimal point. And if you now would do augmentation, then potentially, like when you compute this new improving solution, you might have to go through all these points here, one after another, and so on and so forth until you reach this point. And what bitscaling does is, by rescaling the objective, and starting with the highest or the most significant bits first, it makes this jump here, jumps to this point, then we add the next bits, we jump to this point, and so on and so forth until we reach the optimal solution here. And this also is very much reflected now in the convergence analysis, which is more or less quite straightforward now. So the number of restarts that we need is, so we start with mu being basically the largest coefficient in the objective function, and we have to run this down and half mu until it's less than 1. That takes about log largest coefficient many restarts here. And then within each of these restarts phase, we have at most n augmentations. And now we just can plug the bound together. So we see that we reached an optimal solution with at most n times logarithm of the largest coefficient here, plus 1, plus 1. So this is just like for technical reasons. So this basically n times log largest coefficient here, many augmentation steps. And that can be much faster, as you can imagine, than enumerating all the points. And so in particular, if you would take the standard objective where you always double going as you range over the different coordinates, this has an encoding length on a largest coefficient of 2 to the n, so you get an O of n squared complexity versus fully enumerating all 0, 1 points beforehand. What you can also do in general, you can pre-process the C here by some form of approximation argument, so that the log of C that the log of the largest coefficient here in C is always poly n, and by doing so you obtain a strongly polynomial algorithm for optimization here relative to the initial augmentation steps that you need to do where you obtain this improved solution. So that's the guarantee that you obtain. And again, we basically didn't really need to know a lot about integer programming. We just need to assume that we have this initial augmentation oracle, or this initial possibility here to improve a better solution given a current potentially suboptimal solution. And yeah, so that's for the 0, 1 case. We can also do something similar in the integer case, and we arrive at what is called geometric scaling, which is again a restart scheme where we restart via the objective. However, this one is a bit more like regularization. So what we do here is we take the original objective C here, but now we subtract some u times the distance of the point to the starting point of that we use here in the 1 norm, for example. Then we obtain again a restart scheme. It looks very much the same as before. In every round, we call the initial augmentation algorithm. It runs again a linear number of times, and then we halve the mu and we restart, and we get a similar guarantee here. In fact, the guarantee is identical to the bitscaling one in the 0, 1 case, but holds more generally also for integer programs, and just relies on this idea or this oracle that we can make an improvement provided that our initial solution has not been optimal. All right, that's all that I had for today. Thank you very much for your attention.